Hi everyone, welcome back to 2.8. So in 2.6 and 7, we had changed gears a little bit to talk about graphs of functions, but what we're going to do is get back to doing very algebraic based stuff, or calculation based stuff in 2.8 and 2.9. So sections are relatively short. It's not really a ton of new information here, just some new methods, some new things we can talk about. But I wouldn't think that anything here is super scary compared to stuff we talked about, especially in 2.7. So 2.8, two types of things we're going to do. We're going to combine function, and we're going to compose functions. So let's start with combining functions. Well, different ways to combine functions, and they are as follows. F plus g of x. Take a wild guess what this is. And if you said it's just taking two separate functions and adding together, you would be correct. F minus g of x, take a wild guess, taking two functions and subtracting each other. Okay, f times g of x, well, take two functions, multiply them together. F over g of x, take two functions and divide them. Also, you could do g minus f, where you just do g of x minus f of x. G divided by f of x, where you take g of x divided by f of x. Nothing really crazy here, but literally the four ways to combine functions are to add, subtract, multiply, or divide. And then we just introduce some new notation for all four of those. The domain of a combination function is the domain of f intersected with the domain of g. So it's not going to change a whole lot, really. We're not going to spend a whole lot of time doing domains of combination functions. It's not really that exciting. But yes, if you wanted to find the domain of a combination function, you would just take each separate domain and intersect them. The only added restriction we have for this is when we are doing division, we also want to make sure we take out all the values where g of x is 0. If g of x equals 0, then we get something undefined. Not good. So to find domain of any combination function, intersect each part. But if you're doing division, make sure the denominator does not equal 0. Also, if an x value does not appear in the domain of f or g, it cannot reappear in the domain of the combination. So here's what I mean by that. Let's say in f, you can't plug in 1. For whatever reason, you can't plug in 1. But after you do your combination, if you can all of a sudden plug in 1 and you would get something defined, well, you actually can't. Because since 1 wasn't in the original domain of f, it is not able to be in the domain of the combination, whichever combination you're doing. Of course, we're not going to do a ton of domains of combinations here, right? The more interesting part here is actually doing the combinations, at least in my opinion. So not super crazy, but nonetheless, if you wanted to find the domain of something, just make sure that values don't reappear in your domain. So you would plug in x values the same way as you would plug in values for single functions, or you could also plug values into original functions and then do the combination. So for example, if you wanted to do f minus g of 4, this says find f minus g of x and then plug in 4. But also what you can just do is do f of 4 and then subtract g of 4. You would have the exact same effect. All right, so let's do combination functions. All right, let's say f of x, x squared minus 6x plus 8, and g of x is x minus 2. Find all four combinations, plus, minus, multiplication, division, and then plug in x equals 6. Well, let's just start with f plus g of x. F plus g of x says take f of x and add g of x. Well, f of x is right here. G of x is right here. So add those together. Well, negative 6x plus x is negative 5x. 8 minus 2 is 6. And we can simplify that to x minus 2 times x minus 3. And now what I want is f plus g of 6. So wherever we see x, we're going to plug in 6. 6 minus 2 is 4. 6 minus 3 is 3. 4 times 3 is 12. But also, if you're looking for a specific value of your combination, you didn't have to do it this way. So, for example, do we get 12 if we plug 6 into here, 6 into here, and then add them? Well, 6 squared is 36. 6 times 6 is 36. 36 minus 36 is 0. 0 plus 8 is 8. Okay, well, 6 over here, 6 minus 2 is 4. So 8 plus 4, by virtue of, f plus g of x, 8 plus 4 would be 12. So you could also plug values into the originals first, and then do the addition, subtraction, multiplication, division. But I think it is very good algebraic practice to actually do the combination first and then plug the value in. Okay, f plus g of 6. Oh, okay. I didn't realize I had a slide here where I actually do that. So take a second and write this slide down if you want. But yeah, you could also do it this way. All right, f minus g of x says take f of x, subtract g of x. All right, well, only difference here is that now we're going to subtract x, negative 6x minus x, negative 7x, 8 minus negative 2, 8 plus 2, which is 10, which we can factor to x minus 2, x minus 5. Now plug in 6. 6 minus 2 is 4. 6 minus 5 is 1. 4 times 1 is 4. And again, you can do this by plugging 6 into here and then plugging 6 into here, and in this case, subtracting them. Here we said we got 8. Here we got 4. 8 minus 4 is 4. Multiplication, all right. F of x times g of x would be f of x times g of x. And well, if we want to get a nice simplified answer, I wouldn't expand this. I would just factor this one part. And oh, actually, one thing we can do is say x minus 2 times x minus 2, x minus 2 squared. And then if I want f times g of 6, plug in 6 into here. 6 minus 4 is 2. 6 minus 2 is 4. 4 squared is 16. 2 times 16 is 32. Or you could, again, plug 6 into here, plug 6 into here, and then multiply them. 8 times 4 is indeed 32. Let's do division. Alrighty, f of x over g of x. There's f of x, there's g of x. X squared minus 6x plus 8 factors to x minus 2 x minus 2 times x minus 4. And we can cancel out x minus 2. Okay, well, plug in 6. 6 minus 4 is 2. And again, just doing the example of if we plugged it into here originally, plugging 6 into here gave us 8. 6 into here gave us 4. 8 divided by 4 is 2. So multiple ways to do the same thing. All right, let's do the same thing, different functions this time. And now we're going to plug in negative 2. F plus g of x, f of x plus g of x. Here's f of x, here's g of x. Let's combine like terms. And now let's plug in negative 2. Negative 2 squared is 4. 3 times negative 2 is negative 6. And we get negative 1. So not very crazy, I don't think. Subtraction, same thing, except now we're going to subtract. Well, we just get minus 3x. But 2 minus negative 1 is 2 plus 1. And then plug in negative 2. And this is almost getting a little repetitive because we have been plugging in values for a very long time in this class. Okay, f times g of x, f of x times g of x. Take these things, multiply them together. You know what? Don't even bother. This is actually nice and factored for us already. So let's just go right for plugging in negative 2. Negative 2 squared is 4. 3 times negative 2 is negative 6. 4 plus 2 is 6. Negative 6 minus 1 is negative 7. Negative 42. Okay, I don't think this is crazy to many of you watching. If you have gotten to the point of combination functions, you're probably very comfortable, adding, subtracting, multiplying, dividing, as well as plugging numbers in. One more, let's do g over f, because why not? Let's change it up, right? Point is, it doesn't matter what I say. G over f is just g over f instead of f over g. Well, g is now at the top, f is now at the bottom, and now let's plug in 200. 3 times 200 is 600. 200 squared is 40,000. Yeah, why not? I don't know. Just plugging in numbers. Okay, let's do some combination examples, some domain examples of combinations, I should say. So if we want to find the domain of each of the four combinations. Don't forget, three of them are exactly the same. To find the domain of f plus g, f minus g, and f times g, what we're going to do is intersect those domains. Okay, so domain of f of x, x plus 2, the inside has to be greater than or equal to 0. So x is greater than or equal to -2 or -2 to infinity. Domain of g of x would be 5 minus x is greater than or equal to 0. X is less than or equal to 5, however you get there. So everything less than 5. Now, the domain of f plus g, f minus g, f times g is just intersect these. So the intersection of -2 to infinity, -infinity to 5 would be -2 to 5. What do those two domains have in common? Everything between -2 and 5. Now, for f over g, the only added restriction is that we need to make sure that the denominator does not equal 0. Well, g of x can't equal 0. Absolute value of 5 minus x can't equal 0. X just can't equal 5. Before we had -2 to 5. Well, if we now take out 5, it's just -2 to 5 with 5 no longer included. So domain of combinations, kind of weird, right? It's more important that we know how to find domains of functions in general. But yeah, now you can do it with combinations. Well, that's combinations. Let's now do composite functions. They are similar in thinking, but different way we reference them. So composite functions are literally putting one function inside another and simplifying. In combination functions, you are taking two functions and just adding them or subtracting them or multiplying, dividing them. But here in composite, we are plugging functions into other functions. So we have to introduce some new notation. We introduce f of g of x. F of g. And f of g of x says f of x with g of x plugged in. So this outer function with this inner function plugged in. Then we also have g of f. Same thing. We have this outer function with the inner function f of x plugged in. F of f, okay. I joke in my classes saying it's a little cannibalistic, but you know, that's kind of what it is. You're taking f of x and you are plugging f of x into itself. And same thing for g of g. You are taking g of x and plugging it in to g of x. So f of x says take f of x, plug it into itself. G of x says plug in g of x into itself. But at least for f of g and g of f, this is taking one function and plugging it into another function. A little less weird. Okay, another way people mention these functions is fog and goff. So we use this little circle symbol to represent of. So some people like to say this is fog and goff, which if that helps you, by all means do it. It doesn't really help you remember like f of g of x. But I also think it sounds kind of weird when you go to say like foff and gog. I don't know. Those are weird sounding phrases, I guess. I don't know. So however, it helps you remember these, but it's literally just taking this inner function, plugging it into this outer function. If you want to find the domain of a composite function, you would take the domain of the inner function. So here, domain of g, here, domain of f, here, domain of f, here domain of g, right? Whichever one is the inner function. You take the domain of the inner function and you intersect it with the domain of the final composition. All right, let's just do some composition examples. Okay, let's start with f of g of x. F of g of x says f of g of x. So this says wherever we see f, we're going to write g of x. Think back to when we originally started talking about functions. I said that f of potato says wherever we see x, plug in potato. So f of potato would be potato cubed. But now we're not plugging in just some single term. We're not plugging in like x plus h. What we're doing is plugging in g of x. So in f of x, wherever we see x, we're going to write g of x. So f of g of x would be g of x cubed. Again, wherever we see x, write g of x. But then the question is, what is g of x? Well, g of x we have a definition for. G of x is x plus 1. So we get x plus 1 cubed. Notice x plus 1 inside x cubed. But we just got to be very careful with how we talk about that. Some people not some people, some of my students in the past have been able to jump right from here to here. So if this middle step is confusing to you, that's totally fine. It's kind of hard for me to understand why that's why that is. But yeah, if you are not seeing this middle step, but you see this ending step and all the ending steps we're about to do, that's totally fine. Do as you need. Okay, so if we want to plug in x equals 2, f of g of 2 would be 2 plus 1 cubed, 3 cubed, 27. Now, there is actually another way of doing compositions like this. And what it is plug in 2 to g, and then plug that value into f. So doing that same kind of idea, 2 plus 1 is 3. 3 into x cubed is 27. So that's really what's happening. Not really anything crazy in terms of simplification going on here, but that is another way you are able to evaluate. Okay, g of f of x says take g of x, plug in f of x. Well, if this was g of potato, wherever we see x, we would write potato, but now we have g of f of x. So wherever we see x, we're going to write f of x. Okay, well, f of x plus 1, but we have a definition for f of x. F of x is x cubed. Okay, well, x cubed plus 1, now we plug in 2, and we get 8 plus 1, which is 9. Okay. F of x, this is where it starts to get a little funky. That's okay. F of x says wherever we see x, write f of x. Well, if this was f of potato, you would say potato cubed. But if f of x says f of x cubed, wherever you see x, plug in f of x. But what is f of x? F of x is x cubed. So we have x cubed cubed, which is x to the 9th. Well, if we want f of 2, just plug in 2, and 2 to the 9th is 512. 2, 4, 8, 16, 32, 64, 128, 256, 512. There we go. G of x. Okay, g of g says g with g of x plugged in. All right, well, here's g of x. G of potato would be potato plus 1. So g of x is g of x plus 1. But again, we have a definition for g of x, and that is x plus 1. So in total, x plus 2. G of 2 would be 2 plus 2, 4. Very exciting. Okay. So let's find the 4 compositions. We don't need to keep plugging in values. I think we get the idea. But let's find the 4 compositions. F of g of x says f of x with g of x plugged in. F of x is 2x plus 1, but we instead have 2g of x plus 1. And then g of x is x squared minus 3. Let's distribute 2, and negative 6 plus 1 is negative 5. G of f says g of x with f of x plugged in. Well, g of x is x squared minus 3, so g of f of x is f of x squared minus 3. But f of x is 2x plus 1. 2x plus 1 squared, that's foiling, right? Be very careful. 4x squared plus 4x plus 1, and then subtract 2 and factor out 2 just to be fancy. Looking for compositions, we can simplify, but if we're plugging in values, at some point you don't need to simplify. We're just looking for that actual value. F of x says take f of x, plug it into itself. So instead of 2x plus 1, this is 2 f of x plus 1. But f of x is 2x plus 1. Distribute 2 and add. G of g, All right. G of g says take g of x, plug it into itself. G of x is normally x squared minus 3. So the g of x plugged in, we get g of x squared minus 3. But g of x is x squared minus 3 itself. So here we're going to FOIL again and subtract 3. And that's composite functions. Okay, let's do another example. F of g of x says take f of x, plug in g of x, for x squared plus 1. Now for g of x squared plus 1, because we're plugging in g of x, but g of x is 3 minus x. All right, FOIL 3 minus x squared, multiplied by 4, and add. And we can put it back in order. G of f says take g of x, plug in f of x. So instead of 3 minus x, we get 3 minus f of x. F of x, 4x squared plus 1. 3 minus 1 is 2, and negative 4x squared. F of f says take f of x, plug it into itself, for f of x squared plus 1. F of x, though, is 4x squared plus 1. FOIL, multiply by 4, and add. And then g of g says take g of x, plug it into itself. Instead of 3 minus x, we get 3 minus g of x. G of x is 3 minus x. All right. 3 minus 3 is 0. Negative x is positive x. All righty. Let's do some domain stuff. All righty. F of x is 1 over x. G of x is 3x minus 12. If we want to find the domain of f of g of x, this is domain of the inner function g intersected with the final domain. All right. So the domain of the inner function g is all real numbers, right? This is just a polynomial. There's nothing that we can plug in that gets this in trouble. So f of g of x would be 1 over g of x, 1 over 3x minus 12. So what's the domain of 1 over 3x minus 12? 3x minus 12 can't equal 0. X can't equal 4. Everything except 4. So domain of the entire composite function would be negative infinity to infinity intersected with negative infinity to 4 with 4 to infinity. In that case, it's just negative infinity to 4 and 4 to infinity. Okay, so one very brief composite domain example. Not super exciting, but we get the idea. So that's the end of 2.8. We got one more section here in chapter 2 for inverse functions. Inverse functions are actually kind of interesting. It's the same method over and over and over again. So we're going to like that a lot. So I will see you in 2.9. Bye.
Hi everyone, thank you so much for watching. I hope this lecture helped and that you learned something. Just wanted to give the brief disclaimer that this lecture for this section is based on and adapted from the section in College Algebra and Trigonometry, the 4th edition by J.S. Ratty, Marcus McWaters, and Leswowska Zerpek. So just wanted to give that disclaimer. I'm not affiliated with any of the authors. I'm not affiliated with Pearson, the publisher. This is entirely a presentation and lecture I created based on the book. So thank you so much for watching, and see you in the next section.